Hi class, here's our extra practice for Module 3. As you know, Module 3 was quite mathematical, and while we had some R, it was definitely the least R that we've seen so far. So in this extra practice page, while you certainly can use R for a lot of it, I will use very little R. I will be working these problems on my iPad. Very nice, let's get started. Number one, we have a discrete random variable. We're given the probability mass function, except initially we don't know what capital A is. We have the support here, 1, 2, 3, 4. First thing, find the constant A. Okay, there's two properties. You can tell looking at the numerator on this set, the numerator is always positive. In particular, capital A will need to be positive. But how we can solve it exactly is using property 2. So we know we need the sum, say x equals 1 to 4 of f of x to be 1. At x equals 1, we have 11 minus 2. At x equals 2, we have 11 minus 4. At x equals 3, 11 minus 6. And finally, 11 minus 8. So all of this over capital A should equal 1. We're almost there. If you add everything in the numerator, we have 16 plus 8, which is 24. Now we see our constant, capital A, must be 24. All right, maybe I will write this over here. So my function is f of x equals 11 minus 2x over 24. Let's fill in the probability mass function. Okay, we have 9 over 24. We have 7 over 24. We have 5 over 24 and 3 over 24. Now, these two, well, I could write in lowered terms, but I'll just leave 24s in my denominator for all 4 of these. Now, capital F of x. Well, let's do a little bit of work here. You see capital F of 1, it's the probability that the random variable is less than or equal to 1. This is just little f of 1, so I can just fill this in, 9 over 24. Capital F of 2, well, this is the probability. I'll write it. Capital X is less than or equal to 2. This would be little f of 1 plus little f of 2. Either capital X is 1 or capital X is 2. All right, so you notice I just add these two, and I get 16 over 24. Maybe I'll do the work to show one more. Capital F of 3, this would be the probability. Capital X is less than or equal to 3. Well, technically, we have f of 1 plus f of 2 plus f of 3. We add all 3 of these. Or you could just take this number and add this probability. Either way, but you notice we get 21 over 24. Now, finally, the probability, this is just 1. The probability that capital X is less than or equal to 4, this is 1. Okay, I have chosen, as I mentioned, just to leave these unsimplified. It's fine. Next question. Here we have a piecewise defined function. So now I have a continuous random variable. And you notice the support, actually, there's 2 different intervals here. We have the interval -1 to 1, and then the interval 2 to 3. The support is the union of these 2 intervals. All right, letter A, we want to verify little f is a PDF. Well, there's 2 things. Property 1. We can tell by looking at the graph or looking at the function, you see this is greater than or equal to 0 on the support. Now the support is -1 to 1, union 2 to 3. Property 2, Well, this says something about area. I'm not going to integrate it all in this question, in fact. So what we want for property 2, we want this area plus this area to be 1, the integral. Well, I could write it this way, minus infinity to infinity of f of x dx. But really, I'm just going to use geometry to calculate area. Okay, we have this first one. You notice the length here, this is from -1 to 1, is 2, and the height is 1/4. So we have 2 times 1/4. And then here, we have a triangle. The base is 1, the height is 1. Oh, so we have base times height times 1/2. And what do we have? Well, we have a half plus a half. We have 1. This was a fun question. I like thinking about geometry. Now, letter B. We want to calculate 3 different probabilities. We want the probability capital X is bigger than 0. We want the probability that 2 is less than or equal to X is strictly less than 2.5. And finally, we want the probability that minus 0.5 is less than capital X is less than or equal to 2.5. Okay, I'm using geometry on all 3 of these here. First of all, the probability, so let's erase my yellow because I'm going to talk about each one of these as areas. The probability X is bigger than 0. So let's shade it. We want this. Here, area, and this, area. But instead of adding the 2 areas, we could just take 1 minus the probability X is less than or equal to 0. And this part, well, now I can shade in another color, is here. So if we want the area of the turquoise box, well, the base is 1 and the height is 1/4. And so I get 1 minus 1/4, which is 3/4. Now, I'm going to erase all my colors so we can talk about the next one. The next one, we want between 2 and 2.5. So this is all up here. 2 starts here, and then 2.5 is somewhere in between 2 and 3. We would have a little 2.5 right here. So we can calculate this using the area of this triangle. Well, the base is a half. The height, we could evaluate here. 2.5 minus 2, this is also a half. So we have base times height times 1/2. This probability is 1/8. Last part of this number 2, let me once again erase my shading. We want the probability that X is bigger than -0.5 and less than or equal to 2.5. Well, actually, let me put back my shading because I want part of that, but then I need a little bit more here. If this is, say, minus 0.5. Now, just a remark with the continuous random variables, whether there's a less than or equal to, or a strictly less than, it really doesn't matter because we're talking about areas here. So if I did this, I would have the same answer, or if I did this here, I would have the same answer. This is not the case with discrete random variables, but for continuous random variables, probabilities are areas. All right, now we see the area that we wanted. That part of it we calculated above. So we have the 1/8, that is the area here. And I need to add to it the area of this rectangle. Now here the height is 1/4, and this length, well, we go from 1 to minus 0.5. It's 3/2. So we have plus height times, this is 3/2. This is 3/8. So we have 3/8 and 1/8, 4/8, or we can write it as 1/2. I like this question. We had to think geometrically here, or at least the easiest way to go about this was thinking geometrically. Okay, next one. Well, we have a probability mass function, 3 to the x, e to the minus 3 over x factorial. Now, you know, even if it didn't say PMF, we know this random variable is discrete because here. And this is our first example where we see a countably infinite set. The support of this random variable is the non-negative integers. Okay, well, first of all, part A is optional. If you haven't thought about power series in a while, then it might be challenging, but I'm going to do it because I personally love series. Okay, so what do we need in part A? Well, property 1 is more just writing it down. In fact, this is strictly positive. E to the minus 3 is positive. 3 to any power is positive. Factorial is positive. So that's fine. Property 2. What I need is if you add where x goes from 0 to infinity, f of x, I need this to be 1. Whoa, this is the fun part of this question. Well, let me take a step into calculus 2. I'll do this in black. We know the following. The sum, I'm going to use k's here. K equals 0 to infinity. If you take, say, t to the k over k factorial, this is e to the t. This is the Maclaurin series for e to the t, and it converges for all t. Now, if you stare at this, we have this evaluated at 3, but then times a constant. So let me go back over here. We can factor out the constant. Now stare at this and stare at this. All you have to do is replace k with x and t with 3, and we're looking at the exact same thing. So this infinite sum is e to the 3. If you multiply e to the minus 3 times e to the 3, we have e to the 0, which is 1. This is why it's optional, but super fun. Now let me shrink letter A some. Letter B. The probability that x equals 1, we just evaluate this function. So this would be 3 to the 1, e to the minus 3, over 1 factorial. 1 factorial is just 1. So we have 3 e to the minus 3. This is approximately 0.1494. Letter C. This one I'm probably going to use R, so I will show you what I'm doing in R in just a moment. Really, if you wanted to, you could use R for any of these, especially with a function this intricate. But let's talk about this first because it's quite important. If you just try to add, well, so we do not include the endpoints. If you tried to add this, say minus 2, minus 1, 0, 1, 2, 3, 4, that is not correct. In fact, this function is not defined at x equals minus 2. It is not defined at x equals minus 1 as a formula because, well, the factorial is only defined on non-negative integers. So you really need to look at this. So now I'm going to write this here, and then we will switch to R. This is equal to the probability. Well, you have to look in your support so that x runs between 0 I'll put the less than. It's fine. So this would be a sum. X equals 0 to 4 of f of x. That is the important initial step. Okay, now let's look at r. Here's my function. Now, as I was saying, if we tried to evaluate this at, say, -2, we run into an issue. This function is not defined because of the factorial in it. Now, what do we want? We just want to add up the values between 0 and 4. Okay, so the answer is approximately, maybe I'll erase this part, keep what we actually calculated, and then we have this is approximately 81530.8153. Letter D. We want the probability my random variable is bigger than or equal to 2. Well, do you want to calculate this infinite sum from 2 to infinity of this function? You don't have to here. All we need to do, and this is similar to when we did in the last example, just take 1 minus, well, it would be 1 minus the probability that x is, okay, I'll write it. 1 minus the probability that x is less than 2. So we would have 1 minus f of 0, and then also minus f of 1. We can use r if we would like. We have 0.8009. That is the end of this question. Last one, we are back to a continuous random variable, and we can calculate expected value, variance, and then we have a linear transformation of this random variable. Wonderful. So, letter A, we want to calculate the expected value. Now, you could do this in R, but I'm just going to integrate by hand here and use fundamental theorem of calculus. So what is the expected value of y? Well, we integrate over the support. We have y times 1/3 y squared. That's f of y dy. So we are integrating. Let's see, this is 1/3 y cubed. I get 1/12 y to the 4th, and then we evaluate between 2 and -1. So this will be 16/12 minus 1/12, which is 15/12. If you want to write this in lower terms, 5/4. Or you could write it as a decimal. Letter B. Well, first, I think I'll calculate the expected value of y squared. There's more than one way you can calculate variance. In fact, we practice both of these different ways in R. I'll just do it with our shortcut. Expected value of y squared minus the mean squared. So this would be an integral from -1 to 2. We have y squared times 1/3 y squared dy. This is an integral -1 to 2. Well, you notice I have 1/3 times y to the 4th dy. And I have 1/15 y to the 5th, and then we evaluate between -1 and 2. 2 to the 5th is 32. And then we divide by 15. 1 to the 5th is -1. So altogether, I get 33/15, which we could leave like that. It's also 2.2. Maybe I will do it this way. All right, I just move things up so that we're only looking at 4a and B on this page. We have one more part, which is to calculate sigma y squared. In fact, I should not have underlined 2.2. That was just part of my work to get to the variance. Now, we take expected value of y squared minus the mean squared. And this equals 0.6375. Letter C. Well, here's only looking at letter C, but I recopied F, and I also recopied what we just calculated, expected value of y and the variance of y. All right, so now I have x, which is 4y minus 2. Question is, what is the support of x? Well, we look at this interval, so y ranges from -1 to 2. This is the support of y. And so for letter I here, the support of x, okay, let's look at the endpoints. So when y is -1, x is 4 minus 1 minus 2, which is -6. And when y is 2, x is 4 times 2 minus 2, which is 6. Okay, so the support of x, the answer here is this closed interval from -6 to 6. Next part. We had in the fourth lesson of this module, we have formulas for expected value and variance when you have a linear transformation of a random variable. So the expected value of x is the expected value, well, x is 4y minus 2. This will be 4 expected value of y minus 2. Well, we have 4 times 5/4, so we have 5 minus 2. The answer is 3. Then the variance of x, this is 4 squared times the variance of y. It would be 16 times this number, we get 10.2. The third part, here we have to think a little bit because we do not have a probability density function for x. But we can calculate this probability by going back to capital Y. All right, so what we want is the probability that 4y minus 2 is less than -2, right? Because this is capital X. And now you notice you can just add 2. We get the probability for y is less than 0. Another way to say that is the probability that y is less than 0. Now we have something to integrate. So this would be an integral. Y ranges from -1 to 0 of 1/3 y squared dy. And I get 1/9 y cubed. We evaluate between -1 and 0. This will be 0, really plus 1/9. And so my answer is 1/9. I like that last question. It really made us think some, but it was good for us. Okay, thank you so much. This is the end of our extra practice problems, Module 3.